problem, we're asked to figure out how many moles of ice are needed to cool 500 grams of water. And initially it's at about room temperature and it's cooling down to exactly 0 degrees Celsius. And presumably all of my ice melts. Remember, ice is 0 degrees Celsius. Ice water is 0 degrees Celsius as well, but here we're just going to have ice cold water. So we're also given the information over here in yellow. The heat of fusion is 6.020 kilojoules per mole, and the heat capacity is given to us in joules per mole. I sketched a little picture to help us understand the problem. We have a certain amount of ice, and I gave that variable x. That's being added to 500 grams of water at about room temperature. And when the two are mixed, the original water here down on the bottom is 0 degrees Celsius, and the newly created ice water is 0 degrees Celsius. So we have more than 500 grams. We have 500 grams of water down here and a few grams of water up here, but basically the final temperature is 0 degrees Celsius. So it's easier to solve this problem here. Now, what you must kind of take into consideration here is that there's a conservation of energy. The heat gained is equal to the amount of heat loss. So let's write out this here. Heat gained plus heat lost is equal to 0. When ice melts, thermal energy is inputted into it, so we can calculate how much heat is gained by ice melting. And water loses heat if it decreases in temperature. So we have basically two different processes occurring here, and we use this this equation here to figure out what x is at the end of the day. So let's go ahead and calculate here the amount of heat gained. So the amount of heat, I'll just call this process 1 here. The amount of heat is equal to the heat of fusion times the moles of ice. Okay, the heat of fusion is given to us up here. And the moles we just said was variable x. Okay, so it's 6.020x. For now, that's all we can really say about it. Let's take a look at the other process. We'll call this Q2. Q2 is equal to, we use the warming equation with the heat capacity. So moles times the specific heat capacity times the change in temperature. So there's a couple things we need to think about here. We aren't given moles, we're given grams. So to calculate grams of water, we need to do a conversion. 1 mole of water weighs 18.015 grams. Okay. The heat capacity is given to us per mole, so that's why we had to convert this to moles here, so that the moles and moles would cancel. So the heat capacity is 75.4 joules per mole. Okay, per degree Celsius. And the change in temperature is something we need to figure out. Initially it's 20 degrees C and it cools down to 0. What you need to remember is that the change in temperature is always final temperature minus the initial temperature. Okay, over here look at the arrow. This is the final temperature, which is 0. And the initial temperature is 20 degrees Celsius, the room temperature water. So what we have here is actually minus 20 degrees Celsius. So you need to pay attention to your signs here just for the delta parts, okay? So if we go ahead and calculate this out, we get a value of minus 41,854 joules, or minus 41.9 kilojoules. And we're going to use this value here, kilojoules, because in this part over here, we actually had kilojoules, okay? So we need the kilojoules here and kilojoules here to be compatible. All right. At this point, we want to go back to this original equation that we had set up right here, plug things in, and find out what x is. So again, Q1 plus Q2 is equal to 0. So that's 6.020x minus 41.9 kilojoules is equal to 0. And so from this, x is 6.96 moles, or let's round this to 2 sig figs, 7.0 moles of ice. Okay, I hope all the different steps I've taken here are clear. Thanks for watching.